Thank you. I think this presentation goes well with what's new in minerals. The title was originally What's Hot in Denver, debut of the spectacular blue hemimorphite specimens at the 2020 Denver Mineral Show. But as I think you'll see in just a moment, it's probably better described as what's not in Denver. On Wednesday, September 7th, I received a phone call from a friend, Pete Heckscher, who sent me this photograph of some magnificent hemimorphite specimens that had recently debuted from the Ojuela Mine in Mexico. Now, Ojuela is known for fine-grained botryoidal blue hemimorphites, but large single crystals, and particularly coatings like this, are unheard of. And Pete wanted to know if I knew anything about the find, which I didn't. This was the first photograph that I had seen of them. This was the week of the Denver Mineral Show, or the one of the satellite shows. The main show had been canceled because of COVID, and several dealers had beautiful examples of these blue hemimorphites from Ojuela. This is one of the display cases. Daniel Trinchillo, who was at the Denver show, had actually purchased some of these specimens when they first came out back in August of 2020, and he had seen many examples at the Denver show as he was looking around, and apparently there was a lot of speculation about the origin of the color. Some people were suggesting that it might not be natural. Some people thought that it could be natural chalcanthite or chalcanthite, and others knew that chalcanthite can be synthesized very simply in the laboratory and thought that maybe these were coated with a chalcanthite surface coating that was produced in the laboratory. There were hundreds of specimens being displayed at the Denver show, and some of them quite spectacular, such as this. And as you can see, the price tags were getting quite spectacular as well. Daniel was very curious as to the origin of the color, and so he contacted me that Friday and asked if there were some analytical techniques that we could apply to try to determine what was going on here. I said, well, we can give it a shot. There's several things that I can think of. And so he put together a flat of specimens and sent them out that Friday. On Monday, the 11th, I received the flat in the mail, and these are two of the examples that were in there, very representative of the types of things that were being sold. Some nice matrix specimens here where we could see individual crystals or clusters of crystals. And so what I first did is separated some of the crystals from these specimens and looked at them under the optical microscope. This is about a 50x image of one of the larger hemimorphite crystals, and it was immediately apparent that the blue color was actually due to a surface coating, and that the coating in this particular sample was concentrated along the troughs due to striations on the surface of the crystal or at the boundaries where crystals had grown into one another. Here's a smaller transparent crystal that I separated, and the coloration is obviously heterogeneous and somewhat suspicious. Where several smaller crystals had been in contact with this one and had separated, we can see that the color did not go underneath those, and that the color of richest intensity or greatest intensity was actually at the boundary where those pre-existing crystals had previously been. This almost looks like a wetting surface, as if a dye was applied and that dye concentrated along the crevices of the crystal and the striations or at the grain boundaries where these pre-existing crystals had been, which brought into suspicion the origin of the blue color. Assuming that the surface coating was some sort of mineral or crystalline material, I first looked at it using powder X-ray diffraction. I took several of the hemimorphite crystals that had the thickest coating that I could find and ground those up and X-rayed them. Here we have the resulting data, which are in the black diffraction peaks, and the red diffraction peaks are from a database and a synthetic hemimorphite within that database, the ICDD PDF2 database. Now, what's important to note here is that every peak in our powder diffraction pattern that we collected was perfectly matched with peaks from the hemimorphite in the ICDD database, and no additional peaks were found. So this tells us that all we're seeing by diffraction in our sample is the hemimorphite, and we don't see anything from a possible second mineral, which we thought might be the cause of the color on the surface of these things. Now, it's not surprising given the volume of the blue material. It's a thin surface coating, and I had ground up some fairly large crystals of hemimorphite. Even though the surface coating was relatively thick, I believe the absence of any other diffraction peaks is probably due to the concentration of the blue material in the sample, and not due to its lack of crystallinity. However, that could also be a reason for not seeing anything here. The obvious next step was to turn to something that could focus on the blue material and isolate that from the underlying hemimorphite. And we turned to Raman spectroscopy. We used a Renshaw in vivo Raman spectrometer and microscope. This is the instrument which is housed in Dr. Andy Sommer's lab in the Department of Chemistry and Biochemistry at Miami University. And this is where I normally go to collect Raman data on mineral samples. I contacted Andy to see if I could come over and look at these hemimorphites, and because of restrictions at that time, remember this was in September of 2020, and we were right in the throes of the COVID crisis, he suggested that I just drop off the samples, and since it was only a few analyses, he would run them for me. So Andy took those samples and isolated some of the crystals. This is a large crystal that had a particularly thick coating in the lower portion of it here. So he took this and collected Raman data, first on the thickest portion of the blue material, and then on other areas, including this upper right portion, which, at least in this image, doesn't show any of the blue coating, looks like uncoated white hemimorphite. Within an hour, Andy had collected the data and actually identified what the blue film was. This spectrum here, or these two spectra, the lower portion is the blue film from the hemimorphite specimen. The upper is a material that Andy was very well aware of and was immediately able to match with the blue film, hence giving us an identification. And that material is phthalocyanine blue, a very well-known pigment that has been around since the 1930s and is used in all types of manufacturing, including in the dyeing of blue jeans. Phthalocyanine blue is an organic pigment that is completely synthetic. It's not known to be natural. And the perfect match tells us that the color is not natural in these hemimorphites, but is due to the application of this pigment onto its surface. Here we have three different spectrum. The upper one is the concentrated area on the surface, showing the spectrum from the phthalocyanine blue coating. The bottom is the phthalocyanine pigment standard that Andy used for comparison. And the central spectrum was collected in the upper right-hand portion of the crystal here, where there's no obvious pigment on the surface, but we can still see peaks that don't match hemimorphite, but match the Raman spectrum from the phthalocyanine. So all you need is a very, very thin coating, something that's actually not even optically detectable, and you can identify this material. It's such a strong Raman scatterer, and thus Raman spectroscopy really is the ideal way to determine what you have. Now, it turns out that other laboratories were looking at samples to try to identify the origin of the color, and they got peaks. They've shared the data with us. They got peaks at exactly the right portion of the spectrum for phthalocyanine. However, they were unable to determine what it was. They were going on the assumption that the coating was some sort of mineral, be it natural or synthetic, and they were comparing their spectra to databases of mineral specimens. The problem is phthalocyanine is not a mineral, and so it wasn't in those databases. And I'd asked Andy, how did you so quickly identify what this was? Through complete serendipity, I had given the samples to do Raman analysis to one of the few people in the world that probably could site identify the Raman spectrum of phthalocyanine. It turns out that Andy in a previous life worked for a pigment company and where that actually synthesized this material, and he had done Raman spectroscopy on it enough that he didn't even need to look it up. He could simply tell that's what he was looking at in our blue coating on the hemimorphite from memory. Here are two drawings of the structure of this organic molecule phthalocyanine. It's C32H6. There's a copper atom within the molecule, and it's that copper with the ligation of these lighter elements around it that give the strong blue color. There's also nitrogen in here. And it turns out that phthalocyanine was discovered, as I'd mentioned, in the 1930s. It's extremely stable, and that's why it's used for many applications. It's basically insoluble in most solvents like water, acetone, and alcohol. You can disperse it, but you can't dissolve it using those things. And so some of the early characterization of these samples, people put them in acetone thinking, oh, well, if it's a dye, it'll come off in the acetone. Well, in this particular pigment or dye that was used to color the hemimorphites, that isn't true. We also collected chemical data on the blue material using energy dispersive spectrometry in a scanning electron microscope. This is a characteristic spectrum where we can see the silicon, the zinc, and the oxygen from the hemimorphite, but also distinct copper peaks. Again, that's the copper in the phthalocyanine molecule. There are many things we still don't know about the specimens. For example, how is the pigment applied to give the color? Interestingly, at the time of the debut of the specimens at Denver, several video recordings by the miners who collected the specimens were released, showing pockets with the blue material in situ. These are two photographs from those videos. Now, the videos were of poor quality, but it's pretty obvious that the blue hemimorphite is in place. And so how could that actually occur? Well, we don't know, but we can speculate that the dye or the pigment may have been applied in mass while the mine was flooded. That was one suspicion. It could have also been applied to the individual pockets. That would be more difficult, but anyway, these are some of the things that we haven't answered. But what is certain is that in all of the samples that we've analyzed, the blue color correlates with the presence of the phthalocyanine blue pigment, which is not a natural material. It had to have been put into place. Now, an interesting side note is I had mentioned phthalocyanine is used as a dye for blue jeans as well as many other things. It turns out that one of the largest blue jean manufacturing plants in Mexico is very, very close to the mine in Ojuela. And so there's a ready source for this pigment at that location. Another interesting aspect to these specimens is that when the hemimorphite is in contact with other minerals, for example, this specimen shows calcite at the base, that the pigmentation doesn't seem to be adhering to those other minerals. Now, we haven't done experiments to show why this might be the case, but it's very possible that the surface properties of the calcite are such that the pigment does not adhere to it where the hemimorphite it does. And differential coating is certainly well known, not only synthetically, but naturally as well. However, again, the fact that all of the analyses of the hemimorphite show the presence, very distinct presence in Raman spectroscopy of the phthalocyanine blue suggests that all the specimens that we have analyzed, at least, are created and that the blue color is not natural. Thank you very much.